Hello students, welcome back to our channel Physics Gallery Asha Bino, and this is your Asha teacher coming with the new lecture, a very small lecture of our AC, the painting topic. We have to discuss about two small devices. The first one is a chalk coil and the second one is a transformer. Okay, so today we are going to discuss these two devices related to our AC alternating circuit. And before that, a very good morning to all of my dear students. Is there any doubt related to the already taken topics? If there, please ask it in the comment box. Okay, so today we are going to discuss about a chalk coil. At first, we are going to discuss about a chalk coil. So what is a chalk coil? We can see a small device connected to our tube light in our household circuits. Okay, so what is a chalk? Chalk, chalk is just a series RL connection. It is a series RL connection which is connected to certain devices like tube light in order to reduce the voltage across that tube light or some electrical devices. That is normally for our domestic purpose. The voltage AC voltage given is 220 volt. Okay, 220 volt. But devices like tube light doesn't require such high voltage. They do not want this much high voltage. Okay, they works on a low voltage. So we have to reduce the voltage coming across this tube light. Okay, for that we use a chalk coil. Why we don't use directly a resistance? Why don't we use a resistance? We know if we use a resistance across the tube light connection, as R increases, V is equal to IR, V also increases. Okay, so what happens? The potential drop across the resistance increases. That means, suppose this is our tube light. Okay, this is our tube light. And we have connected a resistance across this tube light. So what happens? What happens when the voltage 220 volt came? If we use a high resistance here, the potential drop across this resistance also increases. For example, it drops somewhat 180 volt. As the resistance increases, the potential drop across the resistance also increases. In series, potential divides, we know that. So, from this 220 volt, 180 volt is taken by, for example, 180 volt is taken by this high resistance, then the remaining 40 volt, if the tube light works in 40 volt, the tube light gets the 40 volt. Okay, clear? That means in order to reduce, at first we have said that our electrical devices like tube light doesn't want this high voltage of 220 volt. Okay, but our domestic circuit always gets somewhat 220 volt AC. If this much high voltage goes through the tube light, it gets damaged. So we have to reduce the voltage across this tube light. Okay, so I've said we commonly use a series RL. Instead of resistance R, we use RL series circuit to this tube light, to this device in order to reduce the voltage across it. Why? Why? Why not we directly use the resistance? If resistance is used, then also the same purpose occurs. 220 volt is coming. If the resistance is high, what happens? The potential across this resistor will be also high. The potential drop across the resistor increases. That means the potential obtained to buy the tube light will be less that we want. So why don't we use a resistance in direct? There is another problem. Voltage decreases across the tube light. We know that. But as the resistance increases, potential increases, and what happens? The wastage of power also occurs because power is equal to VI with cos phi. E into I into cos phi. We know that ERMS, IRMS, cos phi. So if V means E, V means E. Okay. So if the voltage increases, the EMF increases, the power also increases. It causes a wastage of power. If we use an extra resistance, a high resistance in series with our electrical appliance, what happens? The potential across this appliance decreases, that we need, but there is a problem. What is that problem? The power is also increased. There is a lot of wastage of power. Okay, it causes the wastage of power. That's why we can't use a resistor directly here. So what we do, we take an RL circuit. Once more, we are taking our tube light. This is our tube light. And now we are connecting a chalk coil in series to the tube light. What is a chalk coil? It is a combination of a resistor and an inductor in series. This is our chalk. Okay, so this is our chalk coil. So what is the speciality when this is added? Take a high inductance value. Here the resistance value is less, but the inductance value L is high. So when RL is taken, what happens? In RL circuit, we can take impedance Z as R by, impedance Z as root of R square plus XL square. Okay, or Z is equal to root of R square plus L omega the whole square. Okay, in next step we have studied cos phi for our RL circuit is R by Z. Okay, that is R by root of R square plus L square omega square. Also, power is equal to ERMS, IRMS cos phi, or E, I, R by root of, we can write cos phi itself. Okay, ERMS, IRMS cos phi, or the apparent power. ERMS, IRMS cos phi. Okay, this is the connection. Now look, we have taken a less resistance. Okay, we have taken a larger inductance value. As L increases, even though R is less, we have taken a large value of L. What happens? The impedance increases. As the impedance across this increases, the potential drop also increases. Okay, so a lot of potential is dropped by this, and the remaining needed potential is obtained by the tube. Just in this case, okay, somewhat 180 volt is taken by this, because the impedance increases, the potential drop across this RL circuit also increases, then the tube light gains only the required smaller potential. That is okay. And what about the power loss? Listen, if L is greater, Z is greater, impedance is greater. And we know the power factor cos phi is equal to R by Z. For R circuit, for R only, cos phi was 1. Here cos phi value is 1. So power becomes Z into I. There is not at all a factor called as cos phi there. Okay, we have studied it in the case of power. So for RL circuit, as Z increases, L increases, Z increases. As Z increases, what happens to cos phi? Power factor cos phi decreases. When cos phi decreases, power decreases. That is, there is no wastage of power if we connect an inductor resistance circuit, a series circuit, to the tube light instead of a resistance directly to the tube light. Clear? So if resistance is directly connected to the appliance, what happens? Potential drop across the resistance increases, and the appliance get only the required potential. That is okay. But it causes a power loss, wastage of power. Why? As the resistance increases, Potential increases, power also increases because there is not at all a factor called as cos phi. Cos phi is 1 there. Okay, so we cannot take or change that factor. But if we take, so it causes the power loss. But if we take an RL circuit, a series circuit to the appliance, what happens? Increase the inductance value, connect an inductor of larger inductance. As L increases, Z increases. As Z increases, cos phi decreases. As cos phi decreases, power also decreases. Clear? Here L increases, okay, Z decreases. When Z decreases, cos phi, sorry. As L increases, Z increases. When Z increases, cos phi decreases. When cos phi decreases, power also decreases. Clear? That is, we can reduce the voltage of the electrical appliance without wasting the power. Okay, with no wastage of power. That is the purpose of using a chalk coil. Clear? So what is a chalk coil? Tell me, what is a chalk coil? It is just a RL series connection which is connected to the electrical appliance directly. Okay. What happens if RL is taken? You have to take an inductor of chalk coil of greater L value. When L increases, Z increases. When Z increases, what happens? The potential drop across the chalk coil increases, whereas the potential obtained by the electrical appliance is required. Okay, so we have reduced the potential across the tube light that we needed at first. That purpose is over. But as a result of larger Z value, cos phi decreases. If cos phi decreases, the power also decreases. That means the power wastage, the loss in power doesn't occur there. Okay, there is no wastage of power. We use the RL circuit for this purpose. Clear? Okay. Clear. So this is a chalk coil and different types of chalk coils are obtained. There are mainly two types of chalk coils. The first one is called as radio frequency chalk coil. Radio frequency chalk coil. And the second one is called as audio frequency chalk coil. Audio frequency chalk coil. Clear? In radio frequency, we use high frequency AC. Okay, and normally air core is used there. Whereas in audio frequency, it is low frequency AC where iron core is used. Okay, where iron core. So there are several types of chalk coils. Commonly used are radio frequency and audio frequency. In radio frequency, high frequency AC is used, and when high frequency AC is used, there we use the radio frequency, and there we commonly use the air core inside it, and audio frequency means low frequency. There we use the soft iron core. Iron core means soft iron core. Soft iron core. Clear? So this is all about the chalk coil. It is a very small topic related, a small device related to our RL circuit. That is our alternating circuit. Okay, hoping you understood this. So this is chalk coil. And now we are going to one more device. The second device is called as the transformer, which you have heard usually. Okay. So what is a transformer? The second device we have to discuss now is transformer, the last topic of the chapter. So we have to discuss about a transformer. So what is a transformer? It is a device which is used to convert AC voltage. Okay. The first thing we have to think is that transformer works only in AC. It never works in DC. So transformer is a device which is used to convert AC voltage, only AC voltage, not a DC voltage. So a transformer converts AC voltage. That is, low voltage may be converted into high voltage and high voltage may be converted into low voltage. Based on the working, there are two types of transformers. The first one is called as the step-up transformer and the second one is called as the step-down transformer. Okay, so there are two types of transformers, step-up and step-down. What does step-up transformer do? A step-up transformer up means increases, converts low voltage AC to high voltage AC. It converts low voltage AC to high voltage step up. Whereas step down means it converts high voltage AC to low voltage AC. Okay, so what is a step up transformer? A transformer which converts low voltage AC to high voltage AC is called a step up, and a transformer which converts high voltage to low voltage AC is called a step down transformer. Okay, and how this transformer works? A very simple principle, that is, we have discussed throughout this chapter, called as mutual inductance, electromagnetic inductance or mutual inductance. So how it works? Based on the principle of mutual inductance. That means any transformer, whether it is step up or step down, consisting of a soft iron core like this. It consisting of a soft iron core with a large number of turns like this. Okay. Here also there is a soft iron core like this. And one half of the core is taken as the primary circuit. This is taken as the primary circuit or input circuit. Okay. And the other half is taken as the secondary circuit or output circuit. Okay. Clear? Here also, this is primary or input and this is secondary or output. Okay. Primary or input region and this is secondary or output region. Okay. Now, in both step up and step down, the primary and secondary circuit contains copper coils wounded. In step up, we can see the copper coils are wounded like this. And in step down, we can see the copper coils are wounded like this. What is the speciality? We can see the number of turns in secondary is greater than the number of turns in primary. Isn't it? Yes. And in step down transformer, the number of turns in secondary is less than the number of turns in primary. So what is the speciality of this number of turns? Mutual inductance we have studied E is equal to minus N d phi B by dt, induced EMF. Okay, and on solving the equation becomes N A B omega sine omega t, starting of our AC. We have studied this in the first lecture of our AC. E is equal to NAB omega sine omega t. There we can write E is proportional to N. We can write E is proportional to N. As the number of turns in the coil increases, the induced EMF also increases. Listen, here we have provided the low voltage AC. Here the voltage was low. The input was low voltage. If we connect the input circuit like this, and this is the output region where we got the output. This is the representation of output. Here also this is the input of our step down, and here the output is obtained like this. It is also easy. Both of them are easy. So listen. So here we have provided low voltage, low EMF AC. But when it undergoes mutual induction to the secondary coil, so what happens? There the number of turns is greater. As the number of turn increases, the induced EMF also increases. That means here the voltage will be high voltage. Okay, that is, we can write here, this is low voltage, primary EMF, and this is high voltage secondary EMF. Okay, here what happens? ES is greater than EP because the number of turns in secondary is greater than primary. Can you see that? Surely. Very good. Okay, similarly, if we take a step down transformer where the number of turns in secondary is less, N decreases, E decreases. That means here we have provided the high voltage. This was high voltage AC input. But when it undergoes mutual induction and comes out from the secondary, what happens? Where the number of turns was less, EMF reduces, low voltage. That is, here we can write ES is less than EP. This is EP region and this is ES region. Clear? So how it works? It works on the very simple principle of mutual inductance, where we have studied the induced EMF is directly proportional to the number of turns. As the number of turn increases, the EMF increases. As the number of turn decreases, the EMF decreases. In step up, the output will have larger number of turns, more EMF is induced, and output voltage will be greater than the input voltage. In step down, the output has lesser number of turns, secondary number of turns is less. So during mutual induction, the EMF is reduced and output EMF will be less than that of the input. Clear? Okay. So this is how a transformer works. Okay, clear? So we can write here E is directly proportional to N. ES by EP is equal to NS by NP. Clear? Okay. And moreover, this is a very efficient device. Transformer is a very efficient device. And the input power and output power is almost assumed to be same. Is almost assumed, 95% is same. So it is a good device with a very high efficiency. So we will assume that, we are assuming that input power is equal to output power. There is loss, but the loss is very less. So we take almost 100% efficiency, which is not correct. Never 100% efficiency will be obtained, even though it is a very good device with a very high efficiency. So we are assuming the power input is equal to power output. So we can write E primary, I primary is equal to power, E into I. E secondary, I secondary. Okay, in the next step, IP by IS can be taken as ES by EP. Okay, so for this equation now gets converted to, the equation may be taken as ES by EP is equal to NS by NP, number of turns, but equal to IP by IS. Okay, clear? And this ratio is commonly called as the transformer ratio, and it has a name, transformer ratio. Transformer ratio generally represented by the letter E. Clear? Okay. Okay, so what is transformer ratio? EMF across the secondary by EMF across the primary is equal to number of turns across the secondary by number of turns across the primary, equal to current in primary by current in secondary. Clear? Okay, write this much. I have to rub. Okay, so this is our transformer. Hoping you understood. You have drawn the schematic representation of transformer, everything. And now, one more thing. Any device has its own efficiency. Okay, so our power are almost taken to be same, but practically we will take the efficiency of the transformer as, efficiency represented by the letter E as power output by power input. Power input. The normal value is almost 95% something, even though you have to write ES, IS by EP, IP. Practically, there will be small loss, okay, due to the components present in the transformer. Clear? So if you want the efficiency, you have to take P output by P input, ES, IS by EP, IP. Clear? Okay, this is the efficiency. And we have said the transformer is a very good device with a large efficiency, high value of efficiency, everything. Even though it is a very good device, there are certain laws. There are certain laws in transformer. Okay, and now we are going to mention certain laws. Laws in transformer. Okay, the first one is flux leakage. Flux leakage. What is flux leakage? We have said here that the working principle of a transformer is mutual induction. That is, when the AC passes through the primary, it is induced, the flux change in primary is induced in the secondary. But theoretically, it is possible to have the almost 100% of flux induction. Okay, flux change in the first one is, that is, primary is as such induced in the induced in the secondary. But practically it is not at all possible. There is some loss in the flux. There is some loss in the flux change when it is induced to the secondary, and that is called as the flux leakage. Okay. Then we have taken soft iron core. We have taken soft iron core. The soft iron core causes certain hysteresis loss. Yes, we have discussed the hysteresis laws in the topic called as magnetism and matter. Please type magnetism and matter, hysteresis. You will get the topic called as hysteresis. That is, during complete cycle of demagnetization and magnetization, some energy is wasted, some energy is used, which act as the hysteresis laws if we use the soft iron material, because it is a magnetic material. Okay, so when we take the soft iron core, it results in hysteresis laws. Okay, that is, once a flux change is induced in the secondary coil, once a flux change in primary is induced in the secondary coil, there causes certain hysteresis laws. So soft iron using causes the hysteresis laws. Then we have taken the copper wires as the coils in the primary and secondary. When you take the copper or iron wire, whatever may be the metal used, it has certain resistance. Any metal you use, it has certain resistance. So as a result of resistance, what happens? Some power is lost. Okay. So copper or iron resistance also causes its resistance also causes certain loss in transformer. Then there are a lot of metal pieces there which causes eddy current. Have you heard of this eddy current? Type eddy current, electromagnetic induction, physics gallery as you get the topic called as the eddy current. It is also a wastage of current. When metal pieces are linked with the change in the magnetic flux, a circulating current are created called as the eddy current. In order to reduce the eddy current, we can use the laminated core. Okay, so all of these resulting, that is flux leakage, hysteresis loss in soft iron core. Then using the metal wires, we will get resistance. As the resistance increases, the power loss increases, and eddy current. All of these results in certain loss in the transformer. Even though these are certain loss in the transformer, even though there is such loss, the transformer is a good device, effective device. Okay, effective device. Okay, clear. So transformer, even though there are a little bit of losses due to the materials, due to the working principle, everything, but even though it is a very good device. Clear. So we have completed the transformer and also AC coil. This was the painting topic of alternating circuit. So we have completed that also, and in the next lecture we will come with the numericals of alternating circuit. Okay, and after that we will go to the new chapter. So hoping you understood the alternating circuit in detail. Go through the topic 1, 2 or 3 times, then it becomes good, effective, perfect. Okay, so see you in the next video. Till then, a very happy good morning, good evening, or good day. Okay, once more, this is our channel, Physics Gallery Ashabino. See you.